Welcome to the Bodhi Academy. My name is Amsha Klasso, and in today's video we'll continue with our class 11 chapter 6 equilibrium. So previously we learned about all the Bronsted acid bases, Lewis acid bases and their conjugate acids and bases. Now in today's video we'll majorly talk about ionization of acids and bases. So now Arrhenius concept of acids and bases becomes useful in case of ionization of acids and bases, as mostly ionization in chemical and biological system occurs in aqueous medium. So strong acids like perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid and sulfuric acid, they are termed as strong acids because they completely dissociate into their constituent ions in the aqueous medium. Thereby they act as proton donors. So as in they dissociate completely and they are donating their protons, that is H+. Similarly, strong bases like lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide and barium hydroxide are almost completely dissociated into ions in an aqueous medium, giving hydroxyl ions. So these strong bases, they also completely dissociate in aqueous medium to give us OH minus ions. Now, according to the Arrhenius concept, they are strong acids and bases as they are capable of completely dissociating and producing H3O plus and OH minus ions respectively. So now they are saying that Arrhenius constant is very useful. Why? Because here we can easily differentiate between strong acids and strong bases. If one is able to give away its proton by completely dissociating, that is if it's giving a H plus proton, then we can say it is a strong acid, and if one of them is giving a OH minus ion or OH minus ions itself, then we can call them as strong bases. Alternatively, the strength of an acid or base may also be gauged in terms of Bronsted-Lowry concept of acids and bases, wherein a strong acid means a good proton donor and a strong base implies a good proton acceptor. Now the same for the same theory we can even apply Bronsted-Lowry concept, in which what they have said, they have spoken directly in terms of protons, as in the one that is giving a proton is a strong acid, as in the one which is a good proton donor, then we call it a strong acid, and the one which is a good proton acceptor, we call it a strong base. Consider the acid-base dissociation equilibrium of a weak acid H+. Now we are looking at a weak acid. Say we have H+, that is a weak acid, and we have base as water. So what will happen? The conjugate acid, as in this acid will give away its proton. Okay, so it will go and combine with this base, so it will become H3O plus. So this becomes its conjugate acid, and the A, which is A minus, which remains, becomes the conjugate base. Now in section we have seen that the acid dissociation equilibrium is dynamic, involving a transfer of proton in forward and reverse direction. So here they are saying there is a proton transfer that is happening in both the directions. Now the question arises that if the equilibrium is dynamic, then with passage of time which direction is forward. So now if we are saying that the system equilibrium is in dynamic state, it is not moving, in that case which direction are we looking at? Is it a forward direction or is it a backward direction? And even if we are looking at the direction, then what exactly is the driving force that makes it go into the forward or backward direction? Now in order to answer all of these questions, we shall deal into the issue of comparing the strengths of two acids. So now involving the dissociation equilibrium. So to answer these questions, what we do is we compare the two acids involving their equilibrium dissociation. Now consider the two acids, say HA and H3O plus, present in the above mentioned acid dissociation equilibrium. We have to see which amongst them is a stronger proton donor. Whichever exceeds in its tendency of donating a proton over the other shall be termed as the stronger acid, and the equilibrium will shift in the direction of the weaker acid. So what they are saying, whichever one exceeds in its tendency of donating a proton, if whoever is ready to donate a proton over the other, two are there, Ha and H3O plus. If say Ha is exceeding its tendency to donate a proton over H3O plus, okay, then we shall term a stronger acid, we shall term Ha as a stronger acid, and the equilibrium which is there, it will shift in the direction of the weaker acid. Say if Ha is a stronger acid than H3O plus, then Ha will donate the protons and not H3O plus, and the solution will mainly contain A minus and H3O plus ions. So the equilibrium moves in the direction of the formation of the weaker acid and weaker base, because the stronger acid donates a proton to the stronger base. It follows that as a strong acid dissociates completely in water, the resulting base formed would be very weak. That is, strong acids have very weak conjugate bases. So now what we are saying is that when a strong acid dissociates completely in water, the resulting base that is formed, it would be a very weak one, because strong acids are meant to have very weak conjugate bases. Strong acids like perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid and sulfuric acid will give conjugate base ions like ClO4 minus, Cl, Br minus, I minus, NO3 minus and HSO4 minus. In this, all of them have lost one of their protons, which are much weaker bases than H2O. So after losing the proton, all these acids which have now lost a proton, they are said to be much weaker than the base water itself. Similarly, a very strong base would give a very weak conjugate acid. So if we look at the vice versa reaction, a strong base will also give a very weak conjugate acid. On the other hand, a weak acid, say Ha, is only partially dissociated in aqueous medium, and thus the solution mainly contains undissociated Ha molecules. Typically, weak acids like nitrous acid, hydrofluoric acid and acetic acid. It should be noted that the weak acids have very strong conjugate bases. So now if we look at these acids over, these are typically weak acids, but the minute they will dissociate and give away its proton, they will form NO2 minus, fluorine and maybe CH3COO minus. These are known to be very strong conjugate bases because their corresponding acids are weak. For example, NH2 minus, O2 minus and H minus are very good proton acceptors, and thus they are much stronger than the bases H2O. Now, certain water-soluble organic compounds like phenolphthalein and bromomethyl blue behave as weak acids and exhibit different colors in their acid, that is HLN, and conjugate bases Ln minus form. So now here we are talking about two of the water-soluble organic compounds. One is phenolphthalein and bromothymol. So in these, what will happen? Bromothymol blue. Now in these, they behave as weak acids and they exhibit different color, okay, and when if we have these as weak acids, means their conjugate base is going to be very different and very strong. So here we are saying that they have very different, they exhibit different colors in their acidic and in their conjugate base forms. Now, ionization constant of water and its ionic products. Some substances like water, they are unique in their ability of acting both as an acid and a base. So this we have already seen. Till now, here previous examples we have considered water to be a base, but when we were discussing the last theories, in that we also saw how water could act as a acid. Now we have seen this in case of water in section 6.10.2. In presence of an acid, Ha, it will accept a proton and act as a base, while in presence of a base B minus which is there, it will act as an acid and it will donate a proton. In pure water, one H2O molecule, it donates proton and acts as an acid. So if it gives away its proton, it will act as a acid, and another water molecules accept proton and they act as a base. Now the following equilibrium will exist. See, we have water as acid and base. In this, what will it do? It will give away its proton, okay, and this one will accept that proton and it will become H3O plus. So this one becomes its conjugate acid. This one, what it will do? This will accept the proton and therefore it will accept the proton and we will get a conjugate base, that is OH minus. So here what is happening? This one is giving away its electron and this becomes H3O plus. This meanwhile, after giving electron, it becomes OH minus, that is the conjugate base. Now the dissociation constant, here we are representing it by the form of K equals to H3O plus, that is same way the products upon the reactants which are there. Now here the reactants are exactly the same, so we write the reactants only 1. So the concentration of water is omitted from the denominator as water is pure liquid and its concentration remains constant. So H2O is incorporated within the equilibrium constant to give a new constant Kw, which is known as the ionic product of water. So now what we are saying here is that the H2O which is there in the denominator, we are omitting it out. Why? Because this water, since it is liquid and it has a fixed concentration, so therefore this is almost like not having negligible, okay. So therefore we incorporate within the equilibrium constant and we get a new constant that is given by Kw, which is the ionic product of water, in which we are only considering the H plus, that is concentration of the protons, and concentration of OH minus ions. The concentration of H plus has been found out experimentally as to be 1.0 into 10 raised to minus 7 moles at 298 Kelvin. And as dissociation of water produces equal number of H plus and OH minus ions, the concentration of hydroxyl ions which is there, that is OH minus, equals to H plus, and therefore they have a same value at a given temperature of 298 Kelvin. Thus, if we put this value of this 1.0 into 10 raised to minus 7, we end up getting 1 into 10 raised to minus 14 mole square. So the value of Kw is temperature dependent and as it is an equilibrium constant. So here this value will be only obtained at 298 Kelvin. If we shift the temperature here and there, then the value will change. So it is a completely temperature dependent value. The density of pure water is said to be 1000 grams per liter and its molar mass is 18.0 grams per mole. From this, the molarity of pure water can be given as H2O equals to, we take 1000, that is the density of density into the molar mass of water. So that comes around to be 55.55 molar. Therefore, the ratio of dissociation of water to that of undissociated water can be given as, we take down the ratio of this, the equilibrium constant is to 55.55. So that comes to be around 1.8 into 10 raised to minus 9. Approximately 2 into 10 raised to minus 9. Thus, equilibrium lies mainly towards the undissociated water. So now we can distinguish acidic, neutral and basic aqueous solutions by the relative values of H3O plus and OH minus concentration. So now if H3O plus concentration is more, means there is more of acidic solution which is present. OH indicates bases, H3O plus indicates acid. So if the concentration of H3O plus is more, we can say that the given solution is more acidic. If it is neutral, then the concentration of H3O plus and OH minus is going to be equal, and if it is basic, the concentration of OH minus is going to be much more than that of H3O plus. Now let's look at this pH scale. So the hydronium ion concentration in molarity is more conveniently expressed on a logarithm scale known as the pH scale. So now this hydronium ion is H3O plus. So this concentration which is there, it is mostly expressed in terms of in the logarithm scale, that is known as the pH scale. The pH of a solution, it is defined as the negative logarithm to the base 10 of the activity. So it is AH plus of hydrogen ion. In dilute solutions which are like greater than 0.01 molar activity of hydrogen ion, it is equal in magnitude of molarity represented by H plus. So it should be noted that the activity has basically no units and it is just defined as this AH plus is the pH equals to concentration of H plus per mole liter inverse. So from definition of pH, the following can be written as pH equals to, because we are talking in terms of logarithm, there is negative log of AH plus which equals to minus log of concentration of H plus ions. Thus, an acidic solution of HCl, that is say 10 raised to minus 2 mole, will have a pH of 2. Similarly, because see here directly we are looking at acidic solution of H plus, correct? So here if I see, this is what the formula is, what pH equals to minus log of H plus. So now H plus we are saying is 10 raised to minus 2 molar. So if I substitute this value over here, now log of anything raised to log of 10 raised to n will be what? 2n. Okay, 2 log of n, correct? So if I break it down, I'll get minus bracket, this minus will come in front again, minus bracket minus 2 log of 1. So here I will directly get as pH equals to 2, because this minus and this minus will become a plus. So pH will be equal to 2. Similarly, a basic solution of any OH having OH minus as 10 raised to minus 4 and H3O plus equals to 10 raised to minus 4, 10 raised to minus 10 will have a pH of 10. So here also again we are not looking at the concentration of base here, we are only looking at the concentration of the hydronium ion. That is what we are looking. pH, it is the negative algorithm of the hydronium ion, that is the H plus concentration. So here whatever the power is raised here, it will be in its positive terms. So at 25 degrees Celsius, water has a concentration of hydrogen ions of 10 raised to minus 7 molar. Hence pH of water will be 7. So acidic solutions possess a concentration of hydrogen ions which is less than 10 raised to minus 7. So what we can conclude here is that if we are saying less than 10 raised to minus 7, so if the pH is less than 7. So less than 7, whichever solutions have a pH of less than 7 will be acidic. Okay. While basic solutions possess a concentration of hydrogen ion that is greater than 10 raised to minus 7. Thus we can summarize that acidic solution has a pH that is greater than 7, basic will have a pH that is less than 7, and neutral solutions which are there, that is if we talk in terms of water, we know its pH is exactly 7. So it is neither acidic nor basic. Now again let's consider the equation Kw equals to H3O plus OH minus. This equals to, we know, 10 raised to minus 14. Now if we take the negative logarithm on both sides of equation, so we'll say minus log of Kw equals to minus log of product of these two, then we can say that this minus we can apply over here, we can directly write log of H3O plus minus log of OH minus. So equals to minus log of 10 raised to minus 14. So pKw equals to pH plus POH which equals to 14. Note that although Kw may change with temperature variations, in pH with temperature are also small that we often ignore it. So there might be, due to the temperature differences, there might be change in the pH, but it is very small and we consider to ignore it. pKw, it is very important quantity for aqueous solution and it controls the relative concentration of hydrogens and hydroxyl ions as their products is a constant. It should be noted that as pH scale is logarithmic, a change in pH just 1 unit also means a change in H plus by a factor of 10. So any change, even a slight change in terms of pH, we can detect it because it is going to change the overall nature of the solution which is given. When hydrogen ion concentration changes by a factor of 100, the value of pH changes by 2 units. So if you see here at the base we are taking 10. Here if we take it to at the base of 100, then it is going to be increasing by 2 units or decreasing by 2 units. So now you realize why the change in pH with temperature is often ignored. Now, measurement of pH of a solution is very essential as its value should be known when dealing with biological and cosmetic applications. So, here we have a basic, this is the actual pH scale. Okay, so here we are saying that if it is less than 7, then it is basic solution. So this is the neutral point, these are the neutral points, and these are the basic sites, and these are the acidic sites. We can have these strips in various colors which indicate the presence of acidic and basic solutions. So that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.